Many of the problems that we deal with in this class are going to include constant acceleration. Those that don't deal with constant acceleration, we will use energy to analyze them, which we'll take a look at in later chapters. So in this video, let's talk about what it means to have constant acceleration and derive some equations which we can use in situations where we have constant acceleration. So the first thing I want to do before we derive these equations is I want to review the slope-intercept form of the equation of a line, which is y is equal to mx plus b. Now b here is the y-intercept, or the y value of the y-intercept, right? So this value is the value of the vertical axis whenever the horizontal axis is equal to 0. That's the definition of our y-intercept. But if we, since we want to talk about constant acceleration, let's change this to be, instead of a y versus x plot, a velocity versus time plot. So we'll plot velocity in the x direction versus time, in which case this would be the y-intercept, or the vertical intercept would be our value of velocity when time is equal to 0, which we've denoted previously as the initial velocity in the x direction, v naught x. So this b is v naught x. And since we're plotting velocity versus time, we know that our slope is equal to the acceleration in the x direction. And we're no longer plotting y versus x. Instead, we are plotting velocity in the x direction versus time. So our linear equation, when we're plotting velocity versus time, becomes velocity in the x direction is equal to acceleration in the x direction times time, plus some starting velocity in the x direction, which we usually write this then as velocity in the x direction is equal to some starting velocity in the x direction plus the acceleration in the x direction times time. This is a relationship between starting velocity, final velocity, acceleration, and time. And we call this our first kinematic equation, the equation of motion for constant acceleration. Next, I want to review a little bit about what average velocity was. So remember, the average velocity in the x direction would be our change in x position over time. So this is some final x position minus some starting x position divided by time, final time minus, since we've denoted here x naught, this suggests the x at time equal to 0, so our starting time must have been equal to 0. So this is x minus x naught divided by time, which is just some later time. Now, we also have, if we have constant acceleration, so for a constant acceleration, we have our average velocity in the x direction simply being equal to the average of the starting velocity and the final velocity. So this is velocity in the x direction plus starting velocity in the x direction divided by 2. This is just the average of these velocities. As long as we have constant acceleration, this is true. Of course, we know that we have the velocity in the x direction is the same as this, right? This is what we just came up with. So rewriting this, we have our average velocity in the x direction is equal to, and I'm going to flip these around. I should have put v naught x first. This is v naught x plus all this stuff, which is v naught x plus axt, all divided by 2. Now, of course, we have v naught x plus another v naught x. That's 2 v naught x, then divided by 2. So this simplifies down to v naught x plus 1/2 ax times time. This is our average velocity in the x direction. So we have, for average velocity in the x direction, we have this, but it's also equal to this. So we can put these together and we can talk about how displacement varies with acceleration and time and starting velocity. So setting these equal to each other, we have x minus x naught over t is equal to v naught x plus 1/2 axt. Now previously we used delta notation, said x minus x naught was delta x, so I'm going to return back to using that notation. In solving this, we have delta x is equal to v naught x times time plus 1/2 ax times the time squared. And this is the relationship between displacement, starting velocity, acceleration, and time. We can see here, this is our second kinematic equation, but taking a look at these figures, we have, if we started out with a constant acceleration, then we knew that the slope of velocity versus time was a constant, which we knew that meant the slope of displacement versus time was constantly changing the same amount. So we have this curve. And so we could see back from the curves that delta x was a function of the time squared. Actually, it was a quadratic, right? Which is exactly what we see in this second kinematic equation here. And so we have these two kinematic equations, and honestly, we can solve all of our problems with just this one and this one. But sometimes we might not be given time, and we could solve this one for time, plug it into this one, and go from there. But in order to reduce the amount of algebra we need to do, it might be convenient to come up with another kinematic equation which combines these together. So let's take a look and do that here. So let's take a look at these two kinematic equations that we came up with. Vx is equal to v naught x plus ax times time, and also delta x equal to v naught x t plus 1/2 ax times time squared. And let's take a look at this first one here. So let's say that we're not given time. We could solve this one for time, and then we can plug it into this one and come up with another kinematic equation that doesn't include time in it. In case we're not given that, we can save ourselves a little bit of work there. So solving this one for time, we have here time is equal to vx minus v naught x divided by ax. Right? And so then plugging this into here, we have delta x is equal to v naught x times vx minus v naught x over ax plus 1/2 ax times vx minus v naught x over ax squared. Right? So then let's just go through and simplify this down a little bit. You see here that we'll have a ax squared on the bottom and ax on the top here. So one of these is going to cancel out. And so this becomes delta x is equal to v naught x minus, it is going to be equal to vx minus v naught x times v naught x all over ax plus 1/2 of, we have here vx minus v naught x squared all over ax. So then I can multiply both sides by acceleration, the x direction, and we can get here ax delta x is equal to v naught x times vx minus v naught x plus 1/2 of vx minus v naught x squared. Then multiplying and expanding, we have here ax delta x is equal to v naught x vx minus v naught x squared plus 1/2 vx squared minus 2 vx v naught x squared, v naught x plus v naught x squared. And then we can see here that we'll have 1/2 times the 2vx v naught x. This would be minus that. We have a positive here. These are going to cancel out. And so we have here ax delta x is equal to negative v naught x squared plus 1/2 vx squared plus 1/2 v naught x squared, which then, so we have minus v naught x squared plus 1/2 v naught x squared. This means that we have ax delta x is equal to 1/2 vx squared minus 1/2 v naught x squared. Multiplying both sides by 2, we have 2 ax delta x is equal to vx squared minus v naught x squared. And so then just rearranging here, we can say that vx squared is equal to v naught x squared plus 2ax delta x. So now we have a kinematic equation which combines the two previous ones together, but does not include time. So in case we're given maybe displacement, acceleration, and starting velocity, we can find a final velocity, or given any of these three, we can find the fourth, and it doesn't depend on time, which is oftentimes very convenient. Yet a fourth kinematic equation I'd like to take a look at. We also can say here, remember that average velocity in the x direction was equal to the starting velocity in the x direction plus final velocity in the x direction divided by 2, as long as we had constant acceleration. But that was also equal to x minus x naught divided by the time. And so then this was delta x. We can solve this, and we can say that delta x is equal to the average velocity v naught x plus vx divided by 2 times the time. So here's a fourth kinematic equation which does not include acceleration. So these are 4 kinematic equations. We could, like I said, we can get everything we need just from those first two, from this one here and this one here, but these last two are convenient combinations of the kinematic equations, which if we don't have time, we can use this. If we don't have acceleration, we can use this.